Hello friends, I am Engineer Sunil Kumar from School of Electrical Engineering and Information Technology, Punjab Agriculture University, Ludhiana. I welcome you all to the video lecture series of Cyber and Information Security. In this lecture, we will study about UDP. First of all, please see the contents which I shall cover. After covering brief introduction about UDP, I shall take up characteristics of user datagram, which will be followed by UDP services. In the last, I shall take up UDP features and UDP packages. So now let us start. UDP is a simple transfer protocol that extends the host-to-host delivery of packets of the underlying network into a process-to-process communication. Since there are many processes running on a given host, UDP needs to add a level of demultiplexing which allowing multiple application processes on each host to share the network. Figure shows the relationship of the user datagram protocol to the other protocols and layers of the TCP/IP protocol suite. UDP is located between the application layer and the IP layer and serve as the intermediary between the application programs and the network operations. A transport layer protocol usually has several responsibilities. One is to create a process-to-process communication. UDP uses port number to accomplish this. Another responsibility is to provide control mechanism at the transport layer. UDP does this task at a very minimal level. There is no flow control mechanism and there is no acknowledgement for received packets. UDP does provide error control to some extent. If UDP detects an error in the received packet, it silently drops it. UDP is a connectionless, unreliable transfer protocol. It does not add anything to the services of IP except for providing process-to-process communication instead of host-to-host communication. UDP is a very simple protocol using a minimum of overhead. If a process wants to send a small message and does not care about reliability, it can use UDP. Sending a small message using UDP takes much less interaction between the sender and the receiver than TCP. Next, user datagram. UDP packets called user datagrams have a fixed size header of 8 bytes. Figure shows the format of the user datagram. The fields are as follows. First, source port number. This is the port number used by the process running on the source host. It is 16-bit long, which means that port number can range from 0 to 65,535. If the source host is a client, the port number in most cases is an ephemeral port number requested by the process and chosen by the UDP software running on the source host. In the source host is the server, the port number in most cases is a well-known port number. Next, destination port number. This is the port number used by the process running on the destination host. It is also 16 bits long. If the destination host is the server, the port number in most cases is a well-known port number. If the destination host is the client, the port number in most cases is an ephemeral port number. In this case, the server copies the ephemeral port number it has received in the request packet. This is a 16-bit field that defines the total length of the user datagram and header plus data. The 16 bits can define a total length of 0 to 65,535 bytes. However, the total length needs to be much less because a UDP user datagram is stored in an IP datagram with a total length of 65,535 bytes. The length field is a UDP user datagram is actually not necessary. A user datagram is encapsulated in an IP datagram. There is a field in IP datagram that defines the total length. There is another field in the IP datagram that defines the length of the header. So, if we subtract the value of the second field from the first, we can reduce the length of the user datagram that is encapsulated in an IP datagram. UDP length equal to IP length minus IP headers length. However, The designers of the UDP protocol felt that it was more efficient for the destination UDP to calculate the length of the data from the information provided in the UDP used datagram rather than ask the IP software to supply this information. We should remember that when the IP software delivers the UDP user datagram to the UDP layer, it has already dropped the IP headers. Next, checksum. This field is used to detect errors over the entire user datagram, that is header plus data. I will discuss the dump example of UDP header in hexadecimal format. The UDP header is CB84000D001C001C. Some questions based on this UDP header. First question, what is a source port number? The source port number is the first 4 hexadecimal digits like CB8416, which means that the source port number is 52100. Next question, what is a destination port number? The answer is that the destination port number is the second 4 hexadecimal digits that are 000D14, which means that the destination port number is 13. Next question, what is the total length of the user datagram? The third 4 hexadecimal digits 001C16 defines the length of the whole UDP packets as 28 bytes. Next question, what is the length of data? The length of the data is the length of the whole packet minus the length of the header, means 28 minus 8 equal to 20 bytes. Next question, is the packet directed from a client to a server or vice versa? Answer, since the destination port number is 13, the packet is from the client to the server. Next question, what is the client process? The client process is the datetime. Next, UDP services. I discussed the general services provided by the UDP in transport layer. First, process to process communication. UDP provides process to process communication using sockets with the combination of IP addresses and port numbers. Several port numbers used by UDP are as follows. Port 7 is for echo, port 9 is for discard, port 11 is for users, port 13 for daytime, port 17 is for quote, port 19 is for chargen, port 53 is for domain, port 67 is for boot PS, port 68 is for boot PC, port 69 is for TFTP, port 111 is for RPC, port 123 is for NTP, port 161 is for SNMP, port 162 is for SNMP trap. Next service is connectionless service. UDP provides a connectionless service. This means that each user datagram sent by UDP is an independent datagram. There is no relationship between the different users datagram even if they are coming from the same source process and going to the same destination program. The user datagrams are not numbered. Also, there is no connection establishment and no connection termination as is the case of TCP. This means that each user datagram can travel on a different path. One of the ramifications of being connectionless is that the processes that uses UDP cannot send a stream of data to UDP and expect UDP to chop them into different related users datagrams. Instead, each request must be small enough to fit into one user datagram. In the case of UDP, only those processes sending short messages when message is less than 65,507 bytes. Next, flow control. UDP is a very simple protocol. There is no flow control and hence no window mechanism. The receiver may overflow with incoming messages. The lack of flow control means that the process using UDP should provide for this service if it is needed. Next, error control. There is no error control mechanism in a UDP except for the checksum. This means that the sender does not know if a message has been lost or duplicated. When the receiver detects an error through the checksum, the user datagram is silently discarded. The lack of error control means that the process using UDP should provide for this service if it is needed. Next, checksum. UDP checksum calculation is different from the one for IP. Here, the checksum includes three sections: a pseudo header, a UDP header, and the data coming from the application layer. The pseudo header is the part of the header of the IP packet in which the user datagram is to be encapsulated with some fields filled with zeros. If the checksum does not include pseudo header, a user datagram may arrive safe and sound. However, if the IP header is corrupted, it may be delivered to the wrong host. The protocol field is added to ensure that the packets belong to UDP and not to TCP. We will see later that if a process can use either UDP or TCP, the destination port number can be the same. The value of the protocol field for UDP is 17. If this value is changed during the transmission, the checksum calculation at the receiver will detect it and UDP drops the packet. It is not delivered to the wrong protocol. Note the similarities between the pseudo header fields and the last 12 bytes of the IP address. Next, congestion control. Since UDP is a connectionless protocol, it does not provide congestion control. UDP assumes that the packets sent are small and cannot create congestion in the network. This assumption may or may not be true today when UDP is used for real-time transfer of audio and video. Next, encapsulation and de-encapsulation. To send a message from one process to another process, the UDP protocol encapsulates and de-encapsulates the messages. First, encapsulation. When a process has a message to send through UDP, it means the message to UDP along with the pair of socket addresses and the length of data. UDP receives the data and adds the UDP header. UDP then passes the user datagram to IP with the socket addresses. IP adds its own header using the value 17 in the protocol field, which indicating that the data has come from the UDP protocol. The IP datagram is then passed to the data link layer. The data link layer receives the IP datagram, which adds its own header and passes it to the physical layer. The physical layer encodes the bits into electrical or optical signals and send it to the remote machine. Next, decapsulation. When the message arrives at the destination host, the physical layer decodes the signal into bits and passes it to the data link layer. The data link layer uses the header to check the data. If there is no error, the header and the trailer are dropped and the datagram is passed to IP. The IP software does its own checking. If there is no error, the header is dropped and the user datagram is passed to UDP with the sender and the receiver IP addresses. UDP uses the checksum to check the entire user datagram. If there is no error, the header is dropped and the application data along with the sender socket addresses is passed to the processes. The sender socket address is passed to the processes in case it needs to respond to the message received. Next, queuing. In UDP, queues are associated with ports. At the client side, when a process starts, it requests a port number from the operating system. Some implementations create both an incoming and outgoing queues associated with each process. Other implementations create only an incoming queue associated with each process. Note that even if a process wants to communicate with multiple processes, it obtains only one port number and eventually one outgoing and one incoming queue. The queues opened by the clients are in most cases identified by ephemeral port numbers. The queues function as long as the process is running. When the process terminates, the queues are destroyed. The client processes can send messages to the outgoing queues by using source port number specified in the request. UDP removes the messages one by one and after adding the UDP header, deliver them to IP. An outgoing queue can overflow. If this happens, the operating system can ask the client processes to wait before sending any more messages. Next, multiplexing and demultiplexing. In a host running a TCP/IP protocol suite, there is only one UDP, but possibly several processes that may want to use this service of UDP. To handle this situation, UDP multiplexes and demultiplexes. First, multiplexing. At the center side, there may be several processes that need to send user datagrams. However, there is only one UDP. This is a many to one relationship and requires multiplexing. UDP accepts messages from different processes differentiated by their assigned port numbers. After adding the header, UDP passes the user datagram to IP. Next, demultiplexing. At the receiver side, there is only one UDP. However, we may have many processes that can receive user datagrams. This is one-to-many relationship and requires demultiplexing. UDP receives user datagrams from IP. After error checking and dropping of the header, UDP delivers each message to the appropriate process based on the port numbers. Next, comparison between UDP and generic simple protocols. We can compare UDP with the connectionless simple protocol. The only difference is that the UDP provides an optional checksum to detect corrupted packets at the receiver side. If the checksum is added to the packet, the receiving UDP can check the packet and discard the packet if it is corrupted. No feedback, however, is sent to the sender. UDP is an example of the connectionless simple protocol with the exception of an optional checksum added to packets for error detection. Next, UDP features. We briefly discuss some features of UDP and their advantages and disadvantages. First, connectionless service. As we mentioned previously, UDP is a connectionless protocol. Each UDP packet is independent from other packets sent by the same application program. This feature can be considered as an advantage or disadvantage depending on the application requirement. It is an advantage if, for example, a client application needs to send a short request to a server and to receive a short response. If the request and response can each fit in one single user datagram, a connectionless service may be preferable. The overhead to establish and close the connection may be significant in this case. In the connection-oriented service, to achieve the above goal, at least 9 packets are exchanged between the client and the server. In connectionless service, only 2 packets are exchanged. The connectionless service provides less delay and the connection-oriented service creates more delay. If delay is an important issue for the application, the connectionless service is preferred. Next, lack of error control. UDP does not provide error control. It provides an unreliable service. Most applications accept reliable services from a transport layer protocol, although a reliable service is desirable. It may have some side effects that are not acceptable to some applications. When a transport layer provides reliable services, if a part of the message is lost or corrupted, it needs to resend. This means that the receiving transport layer cannot deliver that part of the application immediately. There is an uneven delay between different parts of the message delivered to the application layer. Some applications by nature do not even notice these uneven delays, but for some they are very crucial. Next, lack of congestion control. UDP does not provide congestion control. However, UDP does not create additional traffic in an error-prone network. TCP may resend a packet several times and thus contribute to the creation of the congestion. Therefore, in some cases, lack of error control in UDP can be considered an advantage when congestion is a big issue. Next, UDP package. To show how UDP handles the sending and receiving of UDP packets, we present a simple version of UDP package. We can say that UDP package involves 5 components. First, control block table, input queue, a control block module, an input module and a output module. Figure shows the 5 components and their interactions. First, control block table. In our package, UDP has control block table to keep track of the open ports. Each entry in this table has a minimum of 4 fields: the state, which can be free or in use, the process ID, the port number, and the corresponding queue number. Next, input queues. Our UDP package uses a set of input queues, one for each process. In this design, we do not use output queues. Next, control block module. The control block module is responsible for the management of the control block table. When a process starts, it asks for a port number from the operating system. The operating system assigns well-known port numbers to servers and ephemeral port numbers to the client. The process passes the process ID and the port number to the control block module to create an entry in the table for the process. The field for queue number has a value of 0. Note that we have not included a strategy to deal with the table that is full. Next, input module. The input module receives a user datagram from the IP. It searches the control block table to find an entry having the same port number as this user datagram. If the entry is found, the module uses the information in the entry to enqueue the data. If the entry is not found, it generates an ICMP message. Next, output module. The output module is responsible for creating and sending user datagrams. So friends, this was all about UDP. Hope the concepts explained in this lecture were understandable and helpful. Hope to see you in the next lecture. Till then, goodbye. Thank you.